Dear learners, I welcome you all to this online teaching session. Today we will discuss about practicals of subject pharmaceutical analysis 5. To start with practical number 1, that is introduction to multi-component analysis. The basic criteria behind any analytical method is the measurement of some property which is proportional to amount of analyte or concentration of analyte in the sample. Depending upon the property to be measured, these analytical methods are classified as classical methods such as gravimetry, volumetry, titrimetry, etc. and instrumental method such as refractometry, colorimetry, absorptiometry, etc. In present era, market is flooded with various combinations in dosage forms and number is increasing day by day. Sometimes the dosage form in addition to main drugs known to contain other substances which potentially interfere in the assay and if not corrected may impart error to the assay. Hence, development of new methods to analyze these drugs simultaneously without interference is basic need. Now we will learn about multi-component analysis by simultaneous equation method. Uh, you have to consider a multi-component system consisting of two components x and y, each of which absorb at the lambda max of the other. If lambda 1 is lambda max of x and lambda 2 being the lambda max of y, so here in this spectrum we have taken x and y. Lambda 1 corresponds to lambda max of x and lambda 2 corresponds to lambda max of y. In such cases, it can be possible to determine both the components by simultaneous equation method. The information required is the absorptivity of x and x at lambda 1 and lambda 2, that is ax1 and ax2 respectively. The absorptivities of y at lambda 1 and lambda 2, that is a1 and ay2, ay1 and ay2 respectively. So, these absorptivities, that is ax1 and ax2, ay1, ay2 is calculated using standard solution. Then you require the absorbance of diluted sample. Sample means your tablet or dosage form sample or solution of tablet or capsule. So, the absorbance of diluted sample at lambda 1 and lambda 2, that is A1 and A2 respectively. So, if you have these values, that is AX1, AX2, AY1, AY2, capital A1 and capital A2, you can very well calculate Cx and Cy using simultaneous equation method or simultaneous equation. Now, what is that equation? The absorbance of mixture at lambda 1 and lambda 2 can be expressed as capital A1 is equal to AX1 BCX plus AY1 BCY at lambda 1, and it is also expressed as capital A2 is equal to AX2 into BCX plus AY2 into BCY, that is at lambda 2. So, where the B is equal to 1, that is 1 centimeter. So, you can rearrange these two equations and you can calculate the value of Cx, that is Cx can be calculated as capital A2 into AY1 minus capital A1 into AY2 upon AX2 into AY1 minus AX1 into AY2. Similarly, Cy can be calculated as A1 capital A1 into AX2 minus capital A2 into AX1 upon AX2 into AY1 minus AX1 into AY2. So, if you have the value of absorptivity of both the drugs at both the wavelength, and if you have the absorbance of sample at both the wavelength, you can calculate the concentration of both the components. Next is absorption ratio method. It is also known as isoabsorptive point method. This is modification of simultaneous equation method. According to this method, the ratio of absorbance at any two wavelengths for a substance which obeys Beer's law is constant value, and it is independent of concentration and path length. And this constant is also termed as Hofner's quotient or Q value. And because of this method is also known as Q method. So what are the requirements for Q method? You require lambda max of one of the component, that is lambda 2, and you require isoabsorptive point or isobestic point. Now what is that isoabsorptive point? The point where the both components absorb the lambda at which both the components absorb the radiation. So this is the isobestic point, or you can say that the point at which both the absorbance or the absorbance of both the component meet each other. So that is your isobestic point. So this method involves measurement of absorbance at two wavelengths. As I told, lambda 1 is isoabsorptive point, and lambda 2 you can take lambda max of one of the components. Here I have taken lambda 2 as the lambda max of y. You can very well take lambda 2 as a lambda max of x. Now what is the equation? For calculation of component or concentration of components by absorption ratio method, the mathematical equation is Cx is equal to Qm minus Qy upon Qx minus Qy into capital A upon Ax1, and Cy is equal to Qm minus Qx upon Qy minus Qx into capital A upon Ay1. Cx and Cy are the concentration of x and y which we want to calculate respectively. A is the absorbance of sample means tablet or dosage form solution. The absorbance of sample at isoabsorptive wavelength, that is lambda 1. Ax1 and Ay1 are absorptivity of Ax and y at lambda 1, that is isoabsorptive wavelength. Qm can be calculated as it is a ratio of absorbance of sample solution at lambda max of one of the components, that is lambda 2, and absorbance of sample solution at isoabsorptive wavelength, that is lambda 1. Qx can be calculated as it is a ratio of absorptivity of x at lambda max of one of the components, that is lambda 2, and absorptivity of x at isoabsorptive wavelength, that is lambda 1. Qy it is a ratio of absorptivity of y at lambda max of one of the components, that is lambda 2, and absorptivity of y at isoabsorptive wavelength. So in short, Qm is a ratio of absorbance at lambda 2 and lambda 1, and it is the absorbance of sample. So Qm is absorbance of sample at lambda 2 divided by lambda 1, while Qx is the absorptivity of x at lambda 2 divided by lambda 1. Absorptivity at lambda 1, and Qy is absorptivity of y at lambda 2 divided by absorptivity of y at lambda 1. So this is all about introduction to multi-component analysis. Thank you very much for patiently listening.